yesterday we were doing this one, that we are seeing the equivalent conditions for an in the dual graph, right? So G is bipartite. Then every face of a G is an even length, has even length, and the dual graph G star is Eulerian. So these three conditions are equivalent. So we proved one direction, that A implies B, right? That is, if G is bipartite, then we prove that every face has an even length. We use the condition that bipartite graph does not have any odd cycles, right? So next we will prove B implies A. B implies A. So we'll assume that every face has an even length. Then we'll show that that G is bipartite. So let C be a cycle in G. Since G has no crossing, C is laid out as a simple closed curve, right? So since it does not have a crossing, I can draw the cycle as a simple closed curve, right? And since it is a closed curve, there is a region that is enclosed by C. So let F be that region. Let F be the region enclosed by C. Now, every region of the graph of G is wholly within F or outside F, right? Because there is no crossing, so either a region is either inside the F or it is outside the F, where F is the region laid out by the curve, the cycle C, right? Now, if we sum the face lengths, for the regions inside F, we obtain an even number. Even number, since each face has even length, right? So this is our assumption. That is the part B. This is the assumption, right? That every face of G has even length. So when you sum up the face length, then it will be even number. Now, what does this sum count? This sum count each edge of the cycle once, right? Because we are counting the face lengths. So this sum counts each edge of C once. Now it also counts each edge inside the face twice. Each edge inside F twice, since each such edge belong to belong twice to the faces in F. So twice to faces in F. So for example, if we see the previous example that we were saying, this is not exactly an example, but you get an idea. Yes. So while we are counting, this is the closed one, right? So here you can see that this edge was counted twice. So If I go, this is the closed walk. So the total length of the thing was 6, right? Because it is an even walk, right? And in this
mm,
case, this edge was counted twice. So that is what they're saying. So this is our inside region. This is our region F, and this is the closed cycle C, right? So that is more or less an example. So each edge that is on the cycle, they are counted once, but each edge which is inside the region, that is counted twice. So that is the idea.
yeah, yeah.
Twice below index. Hence, the parity of the length, parity of the length of C is the same length, is the same as the parity. Parity means whether it is even or odd. Is same as the parity of the full sum, because the inside the edge is always counted twice, right? So it will always be even. So whether the length of the cycle is even or odd, it only depend that will match with the total sum of the length, right, which is even. So every cycle has even length.
Mm,
So we can conclude that it has to be bipartite, right? Because that is the property of bipartite. So this implies G is bipartite. So this proves A, right? B
mm.
implies A, we proved, right? So this part is clear,
Yeah, yeah. Mm,
right? So now the only part is left is C. So for C, we have to show that the dual graph G star is Eulerian, right? So
yes.
the thing is, so this will be easy because we can follow from part B, because since it has even length, so all the vertex degree will be even, right?
Mm,
Now we know the property of a Eulerian graph. We can verify if all the vertices degree are even, the graph are Eulerian, right?
mm,
So it will directly follow from point B. So we will show B if and only if C. So that will directly follow. So the dual graph is connected because the original graph is connected. The dual graph G star is connected, and its vertex degree
mm,
and its vertex degree are the face lengths. Face lengths of G. Now since the face lengths are even, has total length is even, so this implies degree of V star is even for all V star belongs to the vertex set of G star. So this implies G star is Eulerian,
mm, mm.
right? So this is fine, right?
Even degree even, so that's the
Yes, yes. Because the thing is, what is the degree of the? So if we go back to here for one example, yes. So this is the dual graph. Each face represent my vertex, right? So if the face is bounded by an even cycle, then the degree will be even, right? Because that many edges will come out, right? So for example, here it is an odd cycle, and three edges are bounding this region. So this degree is 3, right? Similarly, here if you see, this is bounded by a four sides, so the degree is 4. So if every region is bounded by even cycle, so the degree of the vertex in the corresponding dual graph will be always be even, right?
mm,
So that's why it is Eulerian. So that is a property, right? If all the vertices are even, then the graph is Eulerian,
mm.
right?
Yeah.
Right. So the next definition is what is an outerplanar graph? So a graph is outer planar if it has an embedding with every vertex on the boundary of the unbounded face. So a graph will say to be outer planar if it has an embedding with every vertex on the boundary of an on the boundary of the unbounded face. Okay. So an outer planar graph an outer planar graph is such an embedding of okay not outer plane graph. An outer plane graph is such an embedding of an outer planar graph.
Outerplanar.
Right. So let me show you an example.
Mm.
1 minute. Let me see an example. Yes. So for example, so if I see this graph, okay. So if I see this graph, then you can see that this is a planar graph. That is fine. So this is one face. This is one face. This is one face, and the outside face is this one. So this is the outside face, right? Then what
Mm.
is the definition is saying that we can actually have an embedding with every vertex on the boundary of the unbounded face. So what is the boundary of the unbounded face? So the boundary of the unbounded face is this is the boundary, right? So this is the boundary of the unbounded face, and you can see that every vertex is on the boundary of the unbounded face, right?
Unboundary where?
Yes, this is the this red highlighted in. This is the boundary of the unbounded face, right? This is the unbounded face. So
Yeah.
you can see that every vertex is on the boundary of the unbounded face. So that is the definition of an outerplanar graph.
Mm.
Okay.
So is it better if we have a symbol of a graph is not
Yes, yes. So for example, yes, yes.
outerplanar,
So if we the thing is yes,
unconnected? Is
yes,
that
yes. No, no. This will be connected. The thing is, so suppose you have this graph.
ah, ah, ah. With the unverted inside?
Yes, yes. If one vertex is inside, means you cannot draw an. So it can happen that you have some.
Mm.
So this is a planar graph, right? So this is a planar graph, but this is not outer planar because the boundary does not have, right. So this is the also this is the smallest planar graph that is not outer planar. So this is an example of an outer planar graph. So the thing is, you cannot have a planar embedding also. So you cannot have an embedding, or you cannot redraw the graph in a different ways as that all the vertices are on the boundary of the face, the external face or the outer face. So yes, so that is the example, right? So the definition is clear, right?
Yeah,
So
yeah, it's okay.
right, so this is the definition. So next is a proposition. So it says the boundary of the outer face of, of a two connected outer plane graph is a spanning cycle. Right. So I know that it is spanning because the thing is all the vertices are there on the boundary. So the proof
Mm.
is not very difficult.
Boundary of outer face of two connected outer plane graph.
Outer face, boundary of the outer face, the face that is not bounded. The outer face of the two connected of a two connected outer plane graph is a spanning cycle.
Two connected.
Yes.
Two connected
So
outer.
minimum two vertices are required to disconnect the graph.
Just a line is a segment.
Yes, yes.
Two connected outer plane is a segment, is right?
Yes, yes. It is the in the statement,
Uh, okay.
right?
Yeah.
Right. So it is a two connected outer plane graph. So it is a spanning cycle, right? So first of all, it is clear that it is spanning because we know, but since it is outer planar, all the vertices lie on the boundary of the outer face. So, so since the graph is outer planar, the boundary
Mm.
of the outer face contains all the vertices. This is by definition.
Mm.
So that part is clear. Now we have to show it is a cycle. So suppose it is not a cycle. So suppose it is not a cycle, then it passes through some vertex more than once, right? So then only it is not a cycle, right?
Mm.
But the thing is, if it passes through more than once, then it would be a cut vertex, right?
Mm.
But this implies such a vertex would be a cut vertex,
Mm. Mm.
right? But that is not the case because we know that the graph is two connected, so it cannot have a cut vertex, right? Because if it has a cut vertex, if you delete, then it becomes disconnected, right? But it is given that it is two connected, but that is a contradiction
Mm.
since the graph is two connected. So it cannot have a cut vertex. So it has to be a cycle. So hence the outer plane it has a spanning cycle. The boundary is a spanning cycle. Okay.
Mm. If it's not a cycle,
Yes.
the boundary of the outer face contains on vertices is okay.
Yes. So if it is not a cycle, so then okay, let me show how does it look like. So so if it is a cycle, then each vertex is coming only once. It is entering and it is going out, right? Now, if it is not a cycle and it is using all the vertices, then it should pass through a vertex more than once. Like means it should happen like this, right? Some type of this should be happen, right? It passes through a single vertex more than once, right?
It is not a cycle, but two cycle is right.
No, no, it is not a cycle, but the graph is connected, right?
Graph connected in outer plane.
Right.
Uh, 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 uh,
So
mm,
outer planar means all the vertices should be in the boundary of the plane. So if it is not a cycle, then a single point, at least one point will have where it will be repeated. The path is repeated, the boundary is repeated, right?
uh, 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 uh.
But then this vertex will act as a cut vertex. If we delete this, it becomes separated the graph. But that is not allowed because we have two connected graph.
Two connected graph. What does it mean? Two
Two
connected.
connected means at least two vertex are needed to disconnect the graph. One vertex cannot. If we delete one vertex, the graph is still connected.
Uh,
Right?
uh, uh. So we can conclude it is not one connected graph is right,
Yes, yes.
but
So
we
it cannot.
cannot conclude this is two or three or n connected.
No, no. The thing is, we don't have to prove it is two connected. I'm saying that prove two connected is given to us. We have to prove that the boundary of the outer face
Okay, 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 okay,
is a
okay.
spanning cycle. That we
Yeah,
have to prove. So we assume that it is not a
it's
spanning
okay.
cycle, and we got a contradiction.
It's okay.
Right.
Mm.
So next one is next proposition is these are the known graphs. K4 is the complete graph on four vertices, and K2, 3 bipartite, complete bipartite. These are planar graph, but not outerplanar. Okay.
Mm.
The thing is, we know that this is planar because by figure, by we can always have a planar embedding of K4 and K23.
Mm.
So planar is not a problem, but we have to only show it
Mm.
is not outer planar.
Ah, ah. Mm. Yeah, 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 yeah.
So
Cái bớt cái Bye Thai 2 3.
yes, yes, there is a complete bipartite 2 3.
Mm.
So this one is K4 that we saw just now, and K23 also we can have an planar embedding. So so this is my K23. So in this K23, these two vertices are in one partition, and these three vertices are in the second partition. So that is the K23. Okay, now we have to show that they are not outer planar.
Mm.
So K4 and K23 both have planar embedding. So implies they are planar. Okay, now to show that they are not outer planar, Observe that they are two connected, right? So they are two connected because you can see that if you delete any one vertex, the graph is still connected, right? So they are two connected. Okay.
Mm. Mm.
So they are two connected. Now by the previous thing,
Ah,
that it
yeah.
has to be the if it is two connected and outer planar graph, then the boundary should be a spanning cycle, right? But let us say, but that will come to a contradiction. But there is no spanning cycle. There is no spanning cycle in K23 because K23 is an a total number of vertices is odd, right? 2 plus 3 is 5, right? But I know that bipartite graph
Mm.
does not have an odd cycle, right? So since it would be a cycle of length 5 in a bipartite graph. So which is a contradiction. So we cannot have a spanning cycle in K23. So K23 is done. So K23 cannot be an outer planar graph. Now in the case of K4, there
Mm.
is a spanning cycle. So
Mm.
there is a spanning cycle in K4, but the endpoints of the two edges, endpoints of the remaining two edges
Mm.
alternate along it. Right. Hence,
Mm.
these chords conflict and cannot be drawn always inside. So hence, these chords conflict and cannot both be drawn inside. So drawing a chord separates a vertex from the outer space.
Mm. Mm.
Vertex. So that's outer planar. It is not possible. So what it is saying is, so it has a spanning cycle. That is, I can draw like this, right? So this is my spanning cycle. But
Mm.
now I have to draw two more edges, right? So I have to draw this edge and this edge, right? But these two edges are alternating because they cross each other, right? So I
Mm.
cannot draw both of them inside. I have to draw one inside and one outside. So once I draw one inside and outside, whenever I try to draw the outside edge, then
Mm.
it does not allow one vertex to be in the outer face, right?
Mm.
It separates the vertex from the outer face. So that's why that property is getting violated, and it is not an outer planar graph, right?
Mm.
So
Yeah, yeah.
up to this part is clear, right? Okay. So the next proposition is, so every simple outer planar graph has a vertex of degree at most 2. That is the statement. Every simple outerplanar graph has a vertex
Mm.
of degree at most 2. Okay.
Every simple autograph has vertex degree at mod 2.
Yes.
Simple autograph, what does it mean?
Simple, normal simple graph. It is
A
no loop.
simple outerplanar.
Outerplanar is outerplanar. That definition that it has a spanning cycle that so it has an outer face. All the vertices are on the outer face,
What's
boundary of the outer
simple?
face.
What's simple? What does it mean?
No, simple is the usual definition, right? It is both simple and outer planar. That is what is saying. So simple graph is that it does not have any loop and multiple edges. That part.
Oh. But previously, when it not cycle, it have one node loop, not loop, one node duplicated. This would be degree 4, is right?
No, I did not get where. Yes, tell again. I did not get.
In the boundary here.
Yes, outer planar graph is every face.
If it's not a cycle, then it's been tossed through some vertices more than one.
Yes,
That means there are some vertices should have degree 4, right?
yes. Degree four that is not a problem, right? It is, but it does not make that it
But
is a loop.
the provision is at most 2.
No, no. Yes, yes. It is saying that degree means it is one vertex that has degree two. So other vertices can be larger, right? It has can
Ah,
have.
okay, okay.
So it has a vertex of degree at most. The remaining
Ah, ah,
vertices can be higher.
okay, okay, okay.
Okay. Okay. So we'll prove for connected graph. So that is sufficient. So it is sufficient to prove for connected graphs, right? So we'll
Mm.
use induction on the number of vertices. Right. So when n is less than equals to 3, that it has, then every vertex has degree at most 2, right? So there is nothing to show.
Mm. Mm.
So every vertex has degree at most 2. So there is nothing to show. Now, if n is greater than equals to 4, we prove a stronger statement. So we prove so what is the statement that G has two non-adjacent vertices of degree at most 2. So we'll show that it has two non-adjacent vertices of degree at most. So they are asking for one vertex, but here we are proving more stronger statement that it has two adjacent vertices, two non-adjacent vertices of degree at most 2. So that will suffice. Okay. So the first step is the basic step when n equals to 4. So n equals to 4, then it is since k4 is not outer planar, so then G has non-adjacent vertices. Then all the vertices are not adjacent to everything, right? G has non-adjacent vertices, and two non-adjacent vertices have degree at most 2, because the highest degree possible is 3, right? In a K in 4 vertices. So if two vertices are non-adjacent, they can be at most 2, right? Two non-adjacent vertices have degree at most 2, right? So now
Mm.
the induction step.
Before in not outer plane we proved.
Yes, yes. K4 is not
And
outer planar. So
yeah,
since it is not outer planar, so G, every vertex will is not adjacent to every vertex, right? In G,
Z has non.
adjacent
What
vertices,
does it mean? I got it point was this year conclude or sin. That's mean when n equal to 4,
right?
z is not k 4.
Yes,
Is
G is not
right.
K4 because yes, because we are
Uh,
considering outer
yeah,
planar graphs. Hmm.
because z is outer
Right,
planar and z is not e4. K4 is not outer planar.
right,
So because z is not k4, z has non urgency vertices.
right,
Oh yeah, and two non vertices. That degree is not two.
right. Because the
Three
what is the
plus
maximum degree in a simple graph? When it is 4 vertices, maximum degree is 3, right? In a simple graph, if the total number of vertices is 4, then maximum degree is 3, right? So if two vertices are non-adjacent, then the maximum degree is 2 becomes
why is for why? Một three. Yeah, okay, okay.
got
Yeah, 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 yeah.
right. So now the induction step. So induction step where n is greater than equals to 4. Then if G has a cut vertex, and then each x lobe of G has a vertex of degree at most 2 other than x.
It love, it love.
Yes,
Forgot.
yes. Yes,
It
I'll
love.
tell you. Other than x.
Um,
And these are non-adjacent in G, right? So x lobe is this one, right? So suppose this is a cut vertex. This is a cut vertex. Then this is how we divide the graph. So this is one lobe and this is one lobe, right?
ah, 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 ah,
Okay.
ah.
So now each part will have a vertex of degree at most 2 by induction, and hence it has two non-adjacent vertices in G, right?
Wait, wait. If I have cut vertices, then it love up the has vertices it up degree 맞죠? 어려라니, 응? Has a vertex is it 맞죠?
Yes. So the card vertex, the S loop definition is clear, right?
어,
Then what do you have? Then the thing is uh, that here. So now the total number of this is a single graph and this is a single graph we can consider, right? This is an outer planar graph and this is an outer planar graph, right? As a thing.
음,
So now we can apply the induction. So here we will have one vertex of degree at most 2 and here we will have one vertex of degree at most 2. So these two are non-adjacent because this is a card vertex.
음. It, so S is degree 2 is right?
No, x
Oh,
x
oh,
can
okay,
be
okay.
x can be
Okay.
anything. We don't know about x.
Yeah, 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 yeah.
Okay.
Mm, it mode too. What are the need? Mm, they are non-agency. They are non-agent. SE okay. It
So
mode
here,
two. Why is
yes.
mode two?
No. The thing is, here will I find one vertex u and one vertex v, right? Because that has
Mm,
degree at most 2. Because if I consider this part, this is an outer planar graph, right? If
mm.
I consider if only this part is an outer plane graph, and by induction I know that this has a single vertex. So by induction, I know that it has a vertex of degree at most 2, right? So that I can apply induction on this part. That is
Here, this step is we assume n
right,
minus
right.
one n.
Yeah.
Okay, 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 okay. Mm-mm.
Right.
Mm-mm.
So
Yeah,
if
yeah.
it is a cut vertex, it is clear. But now if it is two connected, then we have to do separately. So next part is if G is two connected, that is it does not have a cut vertex. If G is two connected, then the outer face boundary is a cycle C.
Mm.
If C has no chords, then G is regular. G is two regular, right? So since it is outer face is a boundary, right? It is two. That is by the last proposition we saw, right? This one, right? If it is a two connected graph, then the outer plane is a spanning cycle, right? So we'll use this proposition. So here what you got is it is two connected and the outer face boundary is a cycle. And if it has no chords, so chord is if you have a cycle, if you have length like this, these are chords, right? So if it has no chords, then it is two regular. That every vertex has degree 2. Then we are done, right?
Mm-mm.
And suppose there is a chord. So the next part is if xy is a chord of C, then the vertex sets of the two xy paths on C both include outer planar subgraphs, right?
Mm-mm. Yeah, yeah. Mm.
Now we can apply the induction hypothesis on this subgraph. So by the
Mm.
induction hypothesis, These subgraphs, suppose H and H prime.
mm,
So let us draw one. So suppose this is the cycle, and suppose you have a chord. So this is my chord xy, right? So this is the chord xy. This is my H and this is my H prime, right? So these are the two subgraphs. So this subgraph H and H prime
mm,
contains vertices. So this is Z, this is Z prime. So contains vertices Z and Z prime of degree at most 2. That are not in xy. So outside these edges x and y. So since no chord
mm,
of C can be drawn outside the cycle of C outside C or cross xy
mm,
because it is outer planar. So so I cannot have any chord outside the cycle because this is the boundary of the outer face, right? It should have all the vertices because it is outer planar. So
mm,
it cannot cross xy, and so we have so this z and z prime, these are not adjacent, right?
mm,
These are not adjacent. So this implies this z and z prime is a required pair of vertices that we are searching. So these are the pair of vertices that has degree at most 2 and then they are non-adjacent. That is what we are searching, right? So this is two non-adjacent vertices have degree at most 2. So this z and z prime will work, and hence it follows for the
mm.
all of the graph, right?
Yeah, yeah, I read again. Yeah, yeah.
Yes, see once.
Mm, mm. We have assumption J has a cut S. Yeah,
Yes.
okay. And the opposite is J has not a cut S. Is right.
Right. Two cases. One has G has a cut vertex, and the second one is it does not have a cut vertex. Then G has
Yeah.
to be two connected.
Two connected. Uh, uh, Previous pro is right.
Yes, two connected will use the previous proposition. Two connected is this one. So
Mm,
if it is a two connected outer planar graph, then the boundary should be a spanning cycle. So this will use.
mm, 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 mm. Then outer phase boundary is cycle. Mm. Yeah. If C has no core.
Chord. If it does not have a
Yeah,
chord,
yeah, yeah.
then
Two
in a
regular is the on what is it? They have 2 degrees, right?
yes, yes, degrees two.
Okay. Mm, that's
So
fine.
this is true, right? Because if it does not have a chord, so this means
Mm,
it is only cycle, right?
mm, mm,
So cycle means every vertex has degree 2, right? So
mm,
it is
mm,
2 regular.
mm. Yeah, yeah.
Yes. So now the
If
next,
have if she have core,
yes, yes. Next case
where
is if G
some
has a chord. So
it
this is the
y
case.
is core.
So this is my chord. Suppose XY is a chord.
Uh, but we don't know how many core is
Yes,
right.
yes. We don't know how many chords are there. So
Hmm.
then,
If K complete, that should be on have core.
yes.
Yeah. The value of two include outerplanar subgraph.
Right.
Hmm. Contain inverted jet graph. Ah, okay. That's it. In induction.
Right.
Not in what? Can you scroll down?
Yes.
Not in HY. Since cause can be drawn outside.
Yes. No chord can be drawn outside because that will contradict the outer planar thing, right? So if I have, suppose one more chord is there, right? So I
Mm.
cannot cross this one and I cannot draw it outside because it is an outer planar graph. So all the vertices should be on the boundary of the outer face, right?
Mm. 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 So we prove that there is one vertex with degree 2,
Right. So
but
this
we
X.
cannot conclude how many vertices degree 2 is, right? At
No, no.
least one.
At least one, yes. But we
Oh,
have proved something more that this part will have one vertex of degree at most 2, and this part will have one vertex of degree at most 2. So now these are not adjacent because the chord cannot cross each other, right?
so we have two.
Right. So we have at least two non-adjacent vertices. So that is what we are trying to prove, right?
So
So
we prove that if the number of vertices greater than 4,
right,
we have at least two vertices with degree 2.
at most 2, yes.
Mm. And not 2.
Right.
That's not exactly 2. It's
Yes,
1
yes.
or
It
2.
can be 1, it can be 2, yes.
How it can be 1?
Yes,
Because
it can be 1 in the case of this cut vertex, it can be 1, right?
cut vertices should be 4, right?
No, no, not cut vertex. I'm saying in the case of the graph, if it is not two connected, if it has a cut vertex, it can be 1 also, right? The degree of u and v, I am saying it need not be 2. That is what I'm saying.
How it can be 1? How it can be 1?
No, no, I'm saying not about x. X can be high degree. I'm saying that these two vertices, what I found out.
Oh, yeah, yeah,
So
yeah. U and V, how can 1?
yes, it can be
Because
just a single edge,
it's
right?
like on the circle, so it should
No, no,
be.
cycle. It is not compulsory, right? It is lie on the cycle. It is not compulsory, right? Because the cycle only comes when it is a two connected, right?
Mm,
The case of a outer cycle that comes only it is a two connected. So you only need outer face, not cycle.
So it should be disconnected, is it right?
No, not disconnected.
Not disconnected, but it's not a cycle, so it's
Yes.
one.
Yes.
If it's a cycle, it should be two.
Yes. Yes. If it is on a cycle, it is true. Yes.
Mm, yeah, yeah.
Okay.
Mm,
Right. So yes. So maybe today we'll stop here then.
yeah, yeah, yeah.
Okay.
Okay. Thank you.